So we have these two results about the subobject classifier, but they're a little abstract. So let's actually see how they work in the category of sets. So I've described how we can find the actual subobject classifier, as in how we can determine its loops as subobjects of Hom E comma blank, and how we can find its vertices as subobjects of Hom V comma blank. And also I've described how we can take these kind of subobjects of Hom functors, which are maximal subobjects, and they're called things like psi E true and psi V true. And those together form this kind of point. Well, we can think of that structure at least as forming a terminal object. And then we can think of this true arrow as being this kind of inclusion function. So just essentially what we're saying in this case is that this loop psi et together with its vertex psi vt, these corresponding respectively to identity Hom E comma blank and identity Hom V comma blank. Well, those two things in this case form this kind of point here, and we can sort of represent this as an arrow from the terminal object, this monomorphism T, this inclusion monic T, and this is really the sort of true arrow pointing into omega. Now, suppose we have an arrow into omega, so this arrow A, for example, and this is coming from some object capital A. So what we want to do is we want to find a subobject that this arrow A classifies. In other words, we want to pull back true along A. In other words, we want to find the inverse image of true along A. Well, we know how to do this in general, but we have a specific theorem for this particular kind of setup, which is our first classifier theorem. And that basically says that we can think of the pullback of true along A here as an inclusion monic, which is coming from an object we call Q, and our previous result informs us that the E figures of Q are going to be the E figures of A, which little a sends to psi of true. Okay, so let's look at the loops, for example. So that means we're looking at the E-type figures, and where is psi E true? Well, there it is. And then we just ask, well, what are all the loops in A which are getting sent to psi E true and the little a? And we find that there's just one of them, which is D. So this informs us that the only loop in Q is just going to be this loop D. Okay, what about the vertices? Well, a sort of similar result to this, but with V's instead of E's, will tell us that all we want to do is find all of the vertices in A that are getting sent to psi V true. And you see that there's just one, and that's just number one, incidentally. And so this is what Q looks like. And then the actual monic that we can consider to be the pullback of true along A is just going to be the kind of inclusion monic of this structure into capital A. And so we can call this A star, or more informatively, we might want to call it A to the minus 1 of T. And then, of course, as usual, we're going to have the actual subobject classified by this. And then, of course, as usual, we're going to have that the classifying arrow of A star is going to be A. But I'm getting ahead of myself a bit there. I still need to sort of explain how we sort of construct classifying arrows so you can see that. In fact, I'm going to demonstrate that. Also, just to mention, I told you we're supposed to have a pullback square here. Well, just to complete it, we're going to have this arrow here, which in fact is just exclamation mark Q, the unique object from Q to the terminal object. And this is going to form a pullback square. So, okay, that's an application of our first classifying theorem. And in a way, there's nothing too fancy about it. As long as we know how to pull back a monic along another arrow, and we know that T is a monic, of course, well, we can already sort of do this. The other thing that's a bit more sort of interesting is this kind of idea. Well, okay, say we have our sub-object classifier, we do, and we have our terminal object, and we have this true arrow, and we also, let's suppose we have some monomorphism, this one M here, from X to A. And what we want to do is find a classifying arrow of M. In other words, we want to find chi of M. So how should we go about doing this? Well, this is actually quite a lot more sophisticated, because it's one thing just to pull back something like true along some arrow. We know how to do pullbacks like that. But we're doing something more particular here. We're actually creating a kind of arrow from A to omega, which has the property that if we pull back true along it, we get M. We're finding the classifying arrow of M. We're finding chi of M. So how do we do it? Well, the way we do it is described. Well, we described it earlier in that classifier arrow, in that classifier theorem too, but here's a kind of succinct description of it. For an object E of C and an element theta of A of E, we define our chi, we define chi M, we define the eth component of it as something that sends theta to the pullback of M along theta under arrow. So remember that like chi M of E, that ought to be some, well, really it's a function from the E-type elements of A to the E-type elements of omega. But remember, we're thinking of the E-type elements of omega as sub-objects of Hom E, blank. And so when we write the pullback of M along theta under arrow, we're sort of saying, well, we have M here, and then when we pick a particular theta, well, I've got a picture of it here actually, but anyway, I'll illustrate this momentarily, but when we pick a particular theta, we illustrate that as an arrow from Hom E, blank into A, this theta under arrow thing. And then what we do is we kind of pull back the monic M along that, and we get a sub-object of Hom E, blank. And that informs us, well, that gives us something in omega, and then we know, because of this kind of prescription here, that that's where chi M of E ought to send theta to. So this is sort of defining how our map's working, how these different functions involved in this natural transformation go. But it's important to realize that we have this sort of funny kind of dual nature to objects, to like E-type elements of omega. We simultaneously think of them simply as members of the set of omega of E, but also as these kind of inclusion monics into Hom E, blank. So, okay, this is going to be a lot clearer once we start doing some examples. So, let's pick an E. Let's actually pick E. We'll talk about loops, and let's pick a E-type element of A. So why don't we think about this D here? Okay, so this is a loop of A, and we're interested in where is this loop going to get sent under chi of M. Okay, under this classifying arrow, which we want to cook up. Now, to cut a long story short, I'll tell you before we actually get into this that really what chi-m is going to do is it's going to send any of the kind of things that are actually fully present in our monic, like such as this D, they're going to get sent to chi-e true and chi something true sort of elements in omega, because they're really corresponding to these kind of maximal subobjects and so on. And once you actually do that, you see that making the rest of the arrow chi-m from A to omega is fairly easy to guess how to do. So, like from a practical perspective, what I'm about to say is a little bit over laborious, shall we say. But anyway, it's nice to be rigorous. So let's do this. So we'll follow our sort of methodology, and we're basically interested in finding what this arrow chi-m, the classifying arrow of this monic M, looks like. So here's how we do it. We want to find out where this chi-m subscript E is going to send D to. Okay, which loop is it going to send it to? Well, our kind of formula from our second theorem here tells us that the eth component of chi-m is going to send D to the pullback of M along D under arrow. So we have D, it's this loop here in A. We form D under arrow, is this arrow from hom E comma blank into A, which is sort of picking out this loop, little D here. And we have this subobject M of A. And what we do then is we pull back M along D. So essentially, when we want to model this as an inclusion monic, all we essentially do is say, okay, let's look at A. The things which are actually in this monic M from A are just this vertex in this loop. And so then we look at all the stuff that D under arrow is sending into A. And in this case, we say, well, all of the stuff which, all of the values of stuff under D under arrow are landing inside this monic. Okay. And whatever stuff under this kind of arrow is landing inside the monic, that's what is sort of defined as being present in this kind of inverse image of M along this arrow. Okay, so in this case, since everything that's getting mapped via D under arrow is landing in M, we have that the pullback of M along D under arrow is just the full subobject of hom E comma blank. And so somehow we're supposed to have that chi-m E of D is equal to this kind of full subobject of hom E comma blank. Well, that's fine, because if we think of this as an inclusion monic, I've already said that we're thinking of the E-type elements of omega of E. We're thinking of those things as though they are subobjects of hom E comma blank. And this process here has indeed yielded a subobject of hom E comma blank. In fact, it's one we know. It's the full subobject of hom E comma blank. It's the identity of hom E comma blank. It's psi et. All right. So To cut a long story short, we know that now chi m is going to send this loop D to psi et. And so we can draw that in. Okay, now let's do the same thing. Oh, and by the way, I said that this loop here is called true. This is sort of the true point, and so that's kind of why this classifying arrow is sending this little d here to this loop, because this loop D here in A is actually inside our monic that we're finding a classifying arrow of. That's why this loop here is getting sent to true. Anyway, let's just carry on. Now let's think about this loop E here. So what's going to happen to that under chi of m? Well, again, our formula says that the eth component of chi of m sends e to the pullback of m along e under arrow. So we form E under arrow. That's picking out this middle loop here. We have this subobject M of A. We pull it back along E under arrow. And so essentially this is just picking out all of the stuff in HOM E comma blank, which got sent to stuff in M under E under arrow. But we see that M basically just involves this vertex 1 and this loop D. It doesn't involve this loop E. And so, like, E under arrow sends the vertex into something that's in M, but it doesn't send the loop into something that's in M. And so the inverse image of M along E under arrow is just this subobject of HOM E comma blank that just contains the vertex and not the edge. In other words, this is what we call chi EM. Okay, it's this subobject of HOM E comma blank which is neither empty nor maximal. And so this is kind of interesting, and we can draw this into our picture. We now know that chi m of E sends E to this loop psi EM. And what this is actually really saying, I mean, what it means when our classifying arrow is sending something to this chi E true loop here. Oh, by the way, I forgot to label this. This is chi E false here. Anyway, just to sort of shortcut this, what it means when our classifying arrow sends something to this sort of chi E true kind of loop here is it means that the place where that kind of map exudes from in A is something that's present in our subobject. And when a loop is sent to this false loop here, chi E false, that means the loop is completely absent and nothing to do with our subobject. But here's a sort of intermediary case, which is sort of neither true nor false. It's like saying, is it true or false that E is in M? Well, it's not completely true. I mean, E is not completely in this subobject M. But then again, it's not completely isolated from it either. The truth is that the vertex of E is present in this subobject, but the loop itself is absent. And this, for us, ends up being a kind of extra truth value. So in fact, there are 3 points of omega in this category of functions here. And so rather than just being a sort of world where things are either true or false, in this case, there can be true, there can be false, and there's also this kind of middle ground here. So, you know, is it true that this loop E is in M? No, but it's not completely false. It's just that the vertex is in M, but the loop itself is absent. Okay, so this is actually modeled by another truth value here, as we see. So we actually have 3 truth values here. It's not just a kind of Boolean system. Anyway, they're things which I don't need to talk about at the moment because we're just computing. Okay, so let's carry on. Now let's work out what happens when we apply our classifying arrow on this loop F here. So once again, our formula tells us that chi_m is going to send F to the pullback of M along F under arrow. So we form F under arrow as this arrow from hom E comma blank into A, which is picking out this loop down here. And then all we do is we just pull back M along F under arrow. And so essentially we're finding all of the stuff in hom E comma blank, which is getting sent to stuff under F under arrow, which is in M, but there's nothing there. Okay, so this is an empty kind of object in this case. And so this result here is an empty object, but remember, the empty subobject of hom E comma blank, for us, we think of this as a member of omega of E, and we call it psi E false. Okay, and so we can draw this in too. F here is getting sent to psi E false. And I mean, at this point, it's absolutely obvious what happens to the vertices. There's only one. In fact, I'll draw it in. It obviously must be the case that vertex 1 is sent to psi v true and vertex 2 is sent to psi v false, because that's the only way that we could have a coherent map that interfaces with these loops as we've already argued that it should. But anyway, let's not let that deter us. Let's actually calculate just so that we see exactly what's happening. So the next thing we want to do, let's pretend that we didn't see how to do that. So we want to work out where 1 is getting maps under this map here, chi_m. So 1 here is a V-type element of A. And so our result says that the V component of chi_m operating on 1 is going to equal the pullback of M along 1 under arrow. So we form 1 under arrow. This is an arrow from hom V comma blank to A, which is picking out this vertex 1 here of A. And then we pull back M along 1 under arrow. And so we're essentially saying what's the subobject of stuff in hom V comma blank, which is getting sent to things inside this monic M. And essentially the answer is, well, everything in here is, okay, because this is just sending something to 1, and we know that 1's in M. So we have that the pullback of M along 1 under arrow is just going to be the kind of full subobject of hom V comma blank, and that's what we call psi V true. And then finally, what about 2? Well, the V component of chi_m operating on 2 is going to equal the pullback of M along 2 under arrow. And so this is going to consist of all the stuff in hom V comma blank that gets sent to things in M under 2 under arrow, but there's nothing there. So this is just going to be the empty subobject of hom V comma blank is going to be our answer. And we know that as psi v false. Okay, so that completes our kind of description of this chi-m here. Now I sort of I have a proof of that this actually is a natural transformation in general, and that it works as the kind of classifying arrow, and all this stuff works. You can see that in the description to the video, but just also notice what I've done here. When I was cooking up this example here, I started with A, and I determined the pullback of true along A, so I determined the sort of sub-object classified by this arrow A. But in this case here, I started with this sort of sub-object, which was actually the same as this one, and I found the classifying arrow of it, chi-m, and of course that ended up being the same as the A in this case. But also notice like the different kinds of functions that this different structure in omega is playing. Okay, notice that this psi false stuff is corresponding to these kind of empty sub-objects, and they're really representing things, and so arrows into those under this things that are getting mapped into these kind of false. So things getting mapped into these kind of E elements of omega, which are representing false, they really represent stuff in A which is not in M, and it's nothing to do with M. On the other hand, E-type elements that are getting sent to psi E true, that are getting sent to this thing corresponding to the kind of full subobject of HOM E comma blank, they are representing things that are fully present and completely contained in this subobject to M. And then there are also these kind of intermediary cases. For example, if we think about a subobject in our category of functions, well, if we pick a loop of that, if we pick a loop of that kind of bouquet, we could say, well, is it true that this bouquet is in this subobject? And the answers can be true, false, or just the vertex is present. And those correspond respectively to something getting mapped to this loop, or this kind of dotted loop, which is kind of representing some kind of intermediate truth value.